I think that we have to move to the last talk, which will be given by Professor Jerzy K. Baksalary from Tadeusz Kotarbiński Pedagogical University in Zielona, Góra. In Finland, the universities get research financing quite a lot also through the Academy of Finland, that gets its financing through the budget as well as the universities do. The Academy of Finland has one form of supporting basic research such that they have 3 research professorships, and the universities can apply those professorships. And we were so lucky that we got that kind of grant that we could invite Professor Jerzy K. Baksalary to work at the Department of Mathematical Sciences. Jerzy has been here since the beginning of last September. I think that those professorships, they are excellent way to support research and also PhD training. When I studied a little bit mathematics when I was a little bit younger than I was now one of my teachers was Dr. Jorma Merikoski, who's sitting over here. And at that time, at the analysis courses, there was also a theoretical examination that was discussing on the topics. There was a written examination, then discussion, maybe 1 hour on the basis of the questions. And I remember when Jorma asked me to define what is a natural number. And now when I have looked and watched and seen how many papers Jerzy has written during his visit to the University of Tampere, I do not know exactly what a natural number for a human being means. But I think that you can see all of those list of those papers in some reports from the Department of Mathematical Sciences. I think that Jerzy has been an excellent support to the university. So the last talk will be, the title of the last talk will be Admissibility and Sufficiency of Linear Estimators in the Gauss-Markov Model. Dr. Baksalary.
Don't need this equipment. Thank you very much, Tarmo. So, the number of these papers can be explained very simply. In comparison to Poland, typewriting machines are much better. So.
You mean in Poland?
No.
We have no typewriting machines.
But I really had here a terrific year, and I would like to use this opportunity to thank very much to the rector of the university and to the chairman of the department, Erkiliski, to Simo Puntanen, for applying appropriately to the academy that I was lucky to get this grant. I think that there's some reason that I am the last speaker of that workshop, but I enjoyed every hour of that workshop. I think that we found the formula of the workshop made each of us much busier than during the usual conference, but we also gained, I think, much more. There's an additional symbol, I think. In each of these 3 Tampere meetings, the keynote speaker was Professor CRL. The results I am going to present are just the results of my cooperation with him. So, actually the title is about sufficiency and admissibility, but yesterday I led a session on a similar problem, and we had a very interesting discussion about so-called natural restrictions. The problem of natural restrictions, should they be taken into account or not, is also reflected in 2 letters which followed on the article by Simo Puntanen and George P.H. Stein, the American statisticians. Their article actually is about the equality between ordinary least squares estimator and the best linear unbiased estimator. But the letters by Ronald Christensen and Dave Harville actually refer to that particular point only, to these natural restrictions. So I will devote some time to our paper, which will appear in JSPI, and is a study of the influence of the so-called natural restriction on estimation problems. Let me start with the model. We consider the Gauss-Markov model. Gauss-Markov means that the dispersion matrix is sigma square V is known except perhaps for a positive scalar sigma square. So this is a difference between Gauss-Markov model and the general linear model, where the dispersion matrix is a combination of several known matrices with unknown scalars. We assume that the consistency condition holds, and one situation which is of course satisfied when V is positive definite is that the range of the design or model matrix is contained in the range. Range is the same as column space of V. And this is our problem. If this inclusion doesn't hold, then the problem of the so-called natural restrictions arises. It may be characterizing that in the simplest situation. And this is just the problem which was considered or discussed in the letters by Ronald Christensen and Dave Harvey. We want Fy to be an unbiased estimator of a given vector k beta. Of course, we assume that k beta is estimable. In this general Gauss-Markov model, which means that we want to have this equality fx beta equal to k beta to be fulfilled for each beta belonging, and here is the point. The problem is, if we want to have this equation satisfied for each p-dimensional vector beta, or we assume to be very clear that there are no additional information in advance. So there are no linear restrictions of the type r beta plus. This is just no additional information. Or should we consider that beta is restricted? Okay, there are several ways of expressing these natural restrictions. Perhaps simplest is that used by Professor Rao in his Journal of Multivariate Analysis 1973 book, and also by Silly and Ziskind. Here, V pair means any matrix whose columns span the orthocomplement of the column space of V. Perhaps a warning here would be interesting. There's an alternative expression given in the article by Feuerberger and Fraser in the Canadian Journal of Statistics 1980, but as it was pointed out by Dietrich von Rosen, it is incorrect. As here is the orthocomplement of the intersection of the column space of X with the column space of V, orthocomplement to the range of X. It is quite easy to construct a counterexample. So this is not a good way to formulate these natural restrictions. There's another possibility exploited by Professor Alalouf, doctoral student of George P.H. Stein at McGill at that time. This expression looks not very nicely, looks very complicated, but they are useful in several situations, and actually we exploited them quite intensively in our study. Okay, so going back to this problem of unbiased estimator, we consider two classes. This is class U of k beta. K beta is any estimable vector of linear parametric functions. And here our interest is in all estimators which satisfy this equation fx beta equal k beta for each p-dimensional vector beta. So we have these two conditions, fx equal to k and lowercase f must be 0. Another class or alternative class, which is always will be denoted by star, is the class of all estimators which are unbiased or which satisfy this equation for all beta coming from this restricted space, restricted by this natural restriction. What is the problem with these natural restrictions is that the right-hand side vector of these linear equations involves random vector. It is constant with probability 1, but actually is known only after observing random vector y. So this creates a lot of logical problems. Okay, and our study is, this is just an example, compare these two classes. This was nothing new in this, because just the classes of unbiased estimators were already compared in the 1973 textbook by Professor Rao. But we extended this kind of study for several other estimation problems. What is the conclusion of comparing these two classes of unbiased estimators? This is obvious because in defining U, we require that the set of linear equations holds for each beta. When defining U star, this condition is weakened, and this set of linear equations is sufficient to hold only for some limited set of beta. So this inclusion is clear. But what is actually important from the point of view of theory of general Gauss-Markov model is that if we find an estimator in this wider class, in the class of all unbiased estimators in the wider sense, then for each such estimator, it is possible to get an estimator from this narrower class which is equal with probability 1. So for any given f star y plus f star from that class, we have another unbiased estimator from the smaller class, and these estimators are equal with probability 1. So from the practical point of view, we may really restrict our attention to the situation where we consider beta to be completely free. And this gives us a lot of comfort. Calculations are easier, and also conceptually this problem, all these estimation problems are easier. Which other problems we consider? We compare best linear or minimum dispersion linear unbiased estimator also in these two versions. What is very nice property discovered in already mentioned Journal of Multivariate Analysis 1973 Professor Rao's paper is that the additional condition in both cases is the same. In order to an unbiased estimator an unbiased estimator fy plus f, here it is unbiased in this narrower sense, here in the wider sense, is best linear unbiased if and only if the range of vf prime is contained in the range of x. And this additional condition is the same in both cases, but it is obtained in a different way, because it is obtained by the requirement that the covariance between given unbiased estimator and every unbiased estimator of 0 is 0. Here we consider the class of all unbiased estimator of 0 in this narrower sense, and here in the wider sense. But this just leads to the same additional characterization. So we have similar answer to the problem. If Fy plus F is blue of k beta in the narrower sense, then it is obviously also blue in this wider sense. But again, this statement that if we have a blue in the wider sense, then it is possible to get an estimator which is equal to that with probability 1. We also compare the classes of several classes of estimators. Okay, let me show this transparency. We compare estimators here from the point of view of matrix risk or in generalized mean square error. And so this is dispersion matrix, so this is vector of bias times its transpose. We define the following classes. Fy plus F is given, and C capital rho is a set of all estimators Gy plus G, which are better in the sense, which have better risk in the sense of Levner ordering than a given estimator Fy plus F. This class is the class of all estimators Gy plus G, which are equivalent, and so on. In any case, we have again unstarred version and starred version of these two classes. And the statement or conclusion is again the same. We have inclusion, but again, for each estimator from this wider class, it is possible to get a representative or a counterpart from a narrower class, which is equal with probability 1. Okay, then we go to admissibility problem, first with respect to matrix risk, and then with respect to mean square error or quadratic risk, and this is of further interest here. So now we consider the usual mean square error, and we will discuss the problem of admissibility of a linear estimator for a given vector of parametric functions k beta from the point of view of, so under quadratic risk. Here we have the usual mean square error, but according to very interesting lemma or theorem by Nobuo Shinozaki in his doctoral dissertation, 1975, we have full freedom in choosing this risk matrix, provided that we are in the class of positive definite matrices. So here we have the risk defined with the use of the identity matrix, using any positive definite matrix, which gives us the same class of admissible estimators. An estimator is admissible if there's in a given class no better estimator with respect to a given risk. And again, we formulate two classes of admissible estimators. One is the class where we require this inequality. This is the usual inequality now to hold for each p-dimensional vector beta. Here, this restriction or this requirement is weakened because we want to have this inequality only for each beta from a set beta beta star. Of course, strict inequality must hold in at least one point. We obtained full characterization of these two classes, and again, we arrived at the conclusion that the class of all admissible estimators for all linear admissible estimators. So admissibility here is understood because this is always a problem. The class of estimators within which comparisons are made is the class of all linear estimators. Of course, there's a version of such problem that we consider admissibility of a given linear estimator within the class of all estimators and so on. But here the problem is as follows. The class of estimators is limited, restricted to linear estimators. We have again inclusion and again the statement that for each admissible estimator in this wider sense, we can find an estimator admissible in this narrower sense, which is equal with probability 1. The conclusion, the overall conclusion from this study is that actually there is no loss in generality in considering beta to be very free. And that was also the conclusion of these two letters which followed Simo and Dior's article. These two authors of these two letters refer to Professor Rao's book because the problem you considered was only unbiased or best unbiased estimation. Here we have a bunch of other problems related to estimation of beta. Okay, so I have 5 minutes. I would like to announce two, I hope, new results concerning admissibility. Let us now restrict to a simple model, simple in the sense that we assume that X is a full column range, so beta is estimable or identifiable in other terminology, and we have here identity matrix as a dispersion. It is known, actually it was shown in Professor Rao's Wald paper, announced 1976, that each linear admissible estimator of beta may be represented as a suitable transformation of the blue. And here we have a characterization of these suitable characterizations. So we transform beta head, which is blue, by a matrix A, which is symmetric with, or which commute with S2 minus 1, or equivalently commute with S, and in addition satisfy this Levner order. During my last visit to a center of multivariate analysis, which is now located at Penn State University, we found that also a kind of reverse statement or converse statement is true. Namely, each linear admissible estimator of beta is actually the blue of the expectation vector under a suitably transformed model. So, having the set of all admissible linear estimators, we actually have a collection of blues. The problem is how to characterize models. Here the problem was how to characterize transformation of the blue. So this is one new result announced here. To announce the second, I need the additional concept, namely linear sufficiency. It is related to the following situation. Suppose that in a given linear model, we have, instead of the original data y, only some transformation of this data. We have Ly. L is a given m by n matrix. The model, the linear model, which is implied by this transformation or which corresponds to this transformation, is of the form Ly is now our random vector with the expectation Lx beta and sigma square LVL prime as the dispersion matrix. Our question is how efficient can we estimate, in our case beta, in our case today beta, using this transform, having this data only. And from the point of view of best linear unbiased estimator, the answer comes through the notion of linearly sufficient statistic, namely Ly is said to be linearly sufficient if, to be short, if the best linear unbiased estimator of x beta can be obtained as a linear transformation of Ly. That was considered in a 1980 paper by Guerriero and Montfort, Econometrica, my joint paper with Radhakrishna, 1981, Annals of Statistics. The term linearly sufficient in this particular sense was introduced by Hilmar Drygas in his Sankhya 1983 paper, which was written during his visit to Indian Statistical Institute in Delhi. There are some other references, including two important, I think, namely a joint paper of Professor Rao with Müller and Sinha in one proceedings volume, and a paper by Professor Rao in another proceedings volume, where we have several alternative ways which lead to the same necessary and sufficient condition for linear sufficiency. There's also a comparison made with the linear sufficiency definition introduced by Barlow. This criterion I mentioned is in the general case of the following form: Ly is linearly sufficient even only if the column space of X is contained, or in our case it would be just we have the dispersion matrix equal to the identity, so the criterion would be that the range of X is contained in the range of L prime. So now I am in a position to show the last transparency, which seems to be very interesting, and this is a result I obtained jointly with my colleague and co-author of several papers on admissibility with Augustyn Markiewicz, who is here. And what is the justification for this result? In two sentences. Namely, this disadvantage of the concept of admissibility, especially in that sense, is that if we take the vector of zeros simply, this is an admissible estimator. This is very, very general criterion. This is the very first reduction of the class of all estimators. So it is nothing especially good that an estimator is admissible. It is only wrong if it is inadmissible. So the disadvantage is that sometimes the reduction of information is too strong. Okay, so our idea is to combine two concepts. Just to have an estimator which is simultaneously admissible but still keeps in so much information that it is possible to produce the best linear unbiased estimator, transforming this vector suitably. So we require that an estimator is admissible and this statistic is linearly sufficient. The answer is as follows. This is if and only if the estimator is of the rich type. And this kind of estimators, here n is any non-negative definite matrix, admissibility of these estimators was shown and considered in already mentioned 1976 paper by Professor Rao, but here we have additional characterization, also the other implication. And this result just finishes my talk. Thank you very much.
Any questions or comments, please?
This last result, the visualization, the real estimators, they are usually boys, right?
Yes, because the class of admissible linear estimators consists of one unbiased, which is just the best linear unbiased, and all the remaining are biased.
Anything else? Dr. Ross.
Models with singularity, another interesting aspect. When B is singular, there are linear functions of y which are constants with probability 1. So that gives us the possibility of considering non-linear functions of y as estimators of parametric functions of theta. For instance, in the usual theory we say when is L prime y is unbiased for t prime beta. Now L we are taking as constant. Now we can make L as functions of those linear functions of y whose variance is 0. Because practically they are constant, but we can make them look like functions of y. So there's another approach to the problem of expectation. As a matter of fact, there is in his presentation somewhere hidden that some of the linear functions he is considering are really not linear in y, they are complicated functions. And they can be written as linear functions of y, but those coefficients themselves are complicated functions of y. And those functions of y are with probability 1 equal to a constant because they are very fixed. And I want to take this opportunity of thanking the organizers of this conference, because all good things must come to an end, and I would like to continue with the excellent lectures from Baksalary and various others we had here. So I would like to particularly thank Professor Pukkila, Professor Kotarbiński, Professor Augustyn, who have put in a lot of work in organizing this conference. We had an excellent and very good performance. So on behalf of myself and on behalf of the audience, I would like to